All right, everybody. So in this video, we are going to do sections 3.1 and 3.2, the first two sections in chapter 3 that we cover. These two sections, especially the first one, are going to lay the foundation for what we're going to see in the next video. The next video has a lot of the actual graphing techniques that we're going to learn about with the calculus. But in this section, especially in this first one, we're going to introduce the idea of maximums and minimums, because there's actually two different ways that we're going to look at that in this class. So to start off, let's go over some definitions. There's going to be a lot of definitions over the next couple sections to kind of be ready for that. So the first definition, if we let c be a number in the domain of a function, then we can say that f of c is either an absolute max or an absolute min based on the following. If an absolute max is defined as the value of f on the domain is always the largest in the domain, which means f of c is always greater than or equal to f of x, versus the absolute minimum says that f of c is always less than or equal to f of x. So in layman's terms, if a function has an absolute max, this is, as you probably guessed it, the highest point. So whatever the highest point on a graph is, that is your absolute maximum if it can be found, and then vice versa of that, your absolute minimum would be the lowest point on the graph that you can find actually as a number. Infinities don't count, and we'll get into that in a minute. Now, there are times that there's more than just an absolute max and min. What if you have what we call a local maximum or min? So a local max or min is defined as, so the definition, the number f of c is considered a local max if f of c is greater than or f of x for every x near c and vice versa for the local min. So how I like to distinguish these two is usually from a picture. So kind of no numbers here, just kind of going face by face. This graph has something of everything that we're going to look at. So I think visually it's going to make a lot more sense what the difference in these two are. So if you look, we've got 5 points we want to talk about: A, B, C, D, and E from left to right. And we want to know what are all of these. So I'm going to start from left to right, and we're going to talk about each of them. So starting with point A. What can we consider that point? Well, if you notice, that point is the lowest point on this graph based on just the picture. So we could actually call this an absolute minimum. We move to point B. As you can see, at this point, the graph changes from going up to going down. So anytime that happens, that is a maximum, but since it's not the highest point on the graph, we don't call this an absolute max. Instead, we will call this a local maximum. Point C, your graph goes from decreasing back to increasing, so you hit a low point. That's going to be a minimum, but once again, it's not the lowest point. We already found the lowest point at A, so since this is not the lowest point on the graph, we call this a local minimum. At point D, kind of like point B, you go from increasing to decreasing, so you create a high point on the graph. Now, since this not only is a local max, it is the highest point on this graph, so we can actually upgrade its name from local max to absolute maximum. That is the highest point on this graph. And finally, point E, we go from decreasing to increasing, so it creates a low point, but it's not the lowest point again. So just like point C, while it's a different spot, we can also call this a local minimum. So that's kind of a way for you to visually see the difference between what a local max and a local min are. All right, some more definitions here. If you ever get to a definition and you need some time to write it down, like I said, just pause the video and my voice will be here when you get back, but I got to make sure I kind of just read through this and go on. So the next definition is called the extreme value theorem, and it says that if f is continuous on a closed interval a to b, then f attains an absolute maximum value and an absolute minimum value somewhere in the interval. Essentially, in layman's terms, this says that if you are given an interval for a function, then you have to have not only an absolute max, but you must also have an absolute min somewhere. It doesn't matter where it's at, but you've got to have it somewhere. Now, the extreme value theorem is illustrated here in figure 8 that I copied out of the book because it kind of illustrates the idea I'm trying to get at. Note that a function can attain an extreme value more than once. Although the extreme value theorem is intuitively very plausible, it's very difficult to prove, and we're not going to worry about showing you why it works. But if you look at all of three of these graphs, they all start at the endpoint A and end at the endpoint B. If you look on the first graph, you can see that your highest point and your lowest point are going to occur either somewhere in the interval, as in figure A. They could, you see your absolute max on the second graph. It is in between, but as we saw on the previous graph, you can have an absolute max or min on the endpoints. So in this case, the endpoint B is actually your lowest point, so we call that the absolute min. And then sometimes it will happen more than once. As you can see on this third graph, there are two different points on the graph that attain the same highest point. They are both called absolute maximums, where once again your absolute minimum may only occur once. There's no set way for you to know that without actually working it out, and I'm going to show you how to do that here in a few minutes. Fermat's theorem, very popular theorem. It says that if f has a local max or min, because remember all absolute max and mins are pretty much local maxes and mins. If f has a local max or min at a c value, then the derivative at c exists, and that means that the derivative is 0. So that means if you can look at a graph and see a local max or min, that means that your derivative equals 0 at that point. But the opposite of that is not always true. Just because the derivative is 0 does not mean that it's going to be a local max or min. And we'll see why as we go through the next few sections. All right, so what is that C value? So maybe some of y'all already knew this, but if not, the C value is defined as what we call the critical number of the function. So the critical number occurs when the following happens, and I'm going to box in both parts. If you take the derivative of the function and set it equal to 0, that's a critical number. Or if you can figure out where the derivative does not exist, which means that usually in this case you have a fraction because the bottom of a fraction can't be 0. Those are two cases that we're going to see throughout the next few sections of how you find critical numbers. Now, the big thing in this section, so the next videos we're going to do all the major details. In this section, I want to do the first one. It's called the absolute max and min stuff. How do you find the highest and lowest point on a function, on an interval given for a function? So remember, the extreme value theorem says that if you're given an interval, you have to have both. So here's what we're going to do in a few minutes. We're going to find the values of f at the critical number. So aka, we are going to find all the c values that I mentioned up here. We're going to find the values at the endpoints, because remember, the endpoints can be your highest and lowest points. And then we're going to compare numbers, and whichever value gives you the largest number, that's your absolute max, and whichever value gives you the lowest number, that will be your absolute min. Well, it may look a little bit confusing kind of just in words, and that's how math usually is. The words confuse you, but as we go through the process, I'm going to walk step by step. How do you find each part here? Before we do the absolute max and min, since we haven't actually technically talked about critical numbers yet, let's do a couple examples. Now, back in the earlier in chapter 2, we talked about how to find horizontal tangent lines. This is essentially the same thing. If you're asked to find the critical numbers, you are going to take the first derivative of your function, and you're going to ask yourself, where does that equal 0? So let's look at our first example. If you have 2x cubed minus 3x squared minus 36x, what are the critical numbers of this function? So step number 1, find the derivative. That would be 6x squared minus 6x minus 36 equals 0. Factor however you need to. I noticed that they all share a 6 in common, so I'm going to factor that out. X squared minus x minus 6 left over. And then hopefully the inside here factors, and it looks like it does. It looks like you're going to factor this into x minus 3 times x plus 2. Set this equal to 0. Now the 6 you don't have to worry about because 6 can't be 0, but I can say that x minus 3 is 0 and x plus 2 is 0, which gives me two critical numbers of x equals 3 and x equals negative 2. This is how you're going to find your critical numbers over the next few sections. And pretty much every section in chapter 3, except for maybe the last one, is going to make you find critical numbers along the way. So just get in the habit of doing this on every problem. You got to also, we don't do a lot of trig in this chapter, but occasionally we have to be able to do some trig problems. So for like part B, if f of theta is 4 theta minus tangent theta, what are the critical numbers of this function? So once again, I'm going to find the first derivative, f prime of theta, which will be 4, oops, not 4 theta, sorry, I almost messed up. Don't do that. So it's just 4 because theta is your variable here. And then minus the derivative of tangent is secant squared. Set that equal to 0. Let's see, I'm actually going to move the secant squared over, that way everything's positive. So 4 equals secant squared theta. I'm going to take the square root of both sides. Now, since we're solving an equation, when you take the square root of both sides, you're actually going to get plus or minus 2 equals secant theta. And then a lot of people don't know their secant values at the top of their head, and that's fine. Just use your reciprocal identity. Secant can be turned into cosine as long as you flip over the value on the left. So instead of being plus or minus 2, it's going to be plus or minus 1/2. And those are values that by this point in the class you should be comfortable with. So for example, if we look at the negative 1/2, and I'll put it in parentheses up here, cosine is negative 1/2 at 2 pi over 3 and 4 pi over 3. That's in quadrant 2 and in quadrant 3. That's where cosine's negative. But cosine is positive 1/2 in quadrant 1 and quadrant 4. That's going to occur at 1 pi over 3 and 5 pi over 3. So this question here actually ended up with 4 critical numbers. And the idea of that plus or minus is going to play a big factor in not only trig problems that we look at, but sometimes when x squareds are by themselves, you have to be ready to do the plus and minus. That way you don't miss any critical numbers, and therefore you don't miss any maximums or minimums. Just be careful there. So the big thing in this section we're going to look at now is let's do that closed interval method. I'm going to, the next, I think it's 3 or 4 problems here, I'm going to give you a function and I'm going to give you an interval. I want you to identify the absolute maximum and minimum values of f. Now, I wrote this in a way that the homework's going to make sense to you. When it says find the absolute maximum and minimum values, your homework only wants the y values. If they say point, then you can give the x and the y in that case. So example number 2. Part A, you have 5 plus 54x minus 2x cubed on the interval 0 to 4. So this first time through this, let's go step by step and talk about what you have to do. Step number 1, you got to find your critical numbers. We just practiced that, so let's do it again. Find the first derivative of your function. The 5 goes to 0, the 54x goes to 54, and then you get a minus 6x squared, and I'm going to set this equal to 0. Do a little arithmetic here, or algebra, whatever you want to call it. I'm going to move the 6x squared over, so 54 equals, 6x squared. Divide both sides by 6. 54 divided by 6, I'm kind of getting ahead of myself, is 9. And here's that plus or minus thing again. When you do the square root of both sides, while you do get an x on the right, the square root of 9 when you're solving an equation is actually plus or minus 3. Now, different people do this next part different ways. Here's actually what I do, is I think it makes the most sense. What I'm going to do is I'm going to take the 2 numbers you just found, negative 3 and 3, and I'm going to plot them on my number line. Then I'm going to also take the endpoints, which are 0 and 4, because those can also be absolute max and mins. And the one thing I will warn you to always check, and some of y'all will catch on to this quicker than others, all 3 of these numbers, or I'm sorry, in this case 4 of these numbers, they all have to be in the interval, but you'll see a problem. That negative 3, that is a critical number. This negative 3 is not between 0 and 4, and that's going to happen from time to time because we can't always look at the perfect interval. That's actually easier for you. You can ignore that number. Now, from here on out, I'm not going to actually write it in the T table. I'm going to notice it up front and just cross it out, but I wanted to show you to always double check yourself in the process. What you're now going to do is you're going to take the other three values, the 3, the 0, and the 4, and you need to plug them into your original function. If you use your calculator, that's fine. Just make sure you get the number correct. So to save a little bit of time on this video, because the last few have been kind of long, I'm going to kind of do these in my head, but you can double check me if you would like. So I have my calculator out here in front of me while I make this video. If I plug 3 into this, so 5 plus 54 times 3 minus 2 times 3 raised to the third, you should get 113. If you plug 0 in, I can do that one pretty quick. Looks like you're going to get 5. And if you plug in 4 the same way that you plugged in 3, you should get 93. So when it asks you to label your absolute max and min values, the 113 is your largest value, so that's going to be your absolute maximum value. The 5 is your smallest value, so that is your absolute minimum value. And that's it. That's how you take a function in an interval and you find the largest and smallest y values in that interval. We're going to do a couple more, just kind of mixing in some different derivative rules. So let's look at part B. If f of t is t squared minus 4 all raised to the third power, what is the absolute maximum and minimum value? Going through the same process again, step number 1, I'm going to find my critical numbers. So I'm going to take the derivative. This is actually going to be a chain rule this time. That means I'm going to bring the 3 to the front. Leave the t squared minus 4 alone, drop the power down to the second power, and then multiply by the derivative of the inside, which is 2t. Before I set this equal to 0, I'm going to clean this up. So 3 times 2t gives me a 6t, and then the t squared minus 4 all squared is the same. And I am going to set this equal to 0. Now, the nice thing about the chain rule is, as we saw back in chapter 2, is that this is already in factored form. So I can go ahead, let me get my different color pen out. We can set both of these equal to 0 separately. So let's do that. I can say that 6t is 0, and I can also say that t squared minus 4 all squared is 0. The first one's really easy to solve. You can divide both sides by 6, and that will give you t equals 0. The one on the right, if you take the square root of both sides, you're going to get a t squared minus 4 on the left. And yes, technically you do get plus or minus 0 on the right, but there's no such thing as plus or minus 0, so we'll just leave it as a 0. Add 4 to both sides, so this is t squared equals 4, and then do the square root property again, and this time you're going to get, you guessed it, plus or minus 2. Now, if you look at those three numbers you found, which one of those fall in the interval you have to check? Well, 0's there, positive 2 is there, but the negative 2, you'll notice, is already one of your endpoints, and there's no need to check it again. So if you would like to, you can actually, just look at t equals 2, because the negative 2, you're going to check it again on the endpoints. So here comes my t chart again. You have x and y. You've got the 0, you've got the 2, and you can call it t if you want to, it's all the same thing. Then I have the endpoints negative 2 and 3. Remember, I omitted the extra negative 2 that we did not need. You're going to plug all 4 of these numbers into the original function. Like I said, if you need to use your calculator, that's fine, but to save some time, I'm going to kind of do this out loud and in my calculator myself over here. So if you plug 0 in, 0 minus 4 is negative 4, and negative 4 cubed should give you a negative 64. If you plug 2 in, 2 squared is 4, 4 minus 4 is 0, and 0 cubed is 0. Negative 2 squared is also 4, 4 minus 4 again is 0, so you actually get 0 twice. And then if you plug 3 in, 3 squared is 9, 9 minus 4 is 5, and 5 raised to the third power is 125. So even though 0 is repeated, and that's fine, neither one of those zeros is anything here. Negative 64 is your smallest number, so that is your absolute min. 125 is your largest number, so that is your absolute maximum value. Very good. Just make sure you can do the chain rule, because it's not going to always just be power rule. All right, the dreaded trig problem. So let's do some trig here. What is the absolute maximum and minimum for 2 cosine of x plus sine of 2x on the interval 0 to pi over 2? So don't change your techniques here. Just the trig's may cause a problem for a few of y'all, but we'll get through it together. We're going to first find our critical numbers. So we're going to say f prime of x is equal to, the derivative of cosine is negative sine, so that's negative 2 sine of x. Sine of 2x is going to be a chain rule because the sine of 2x becomes cosine of 2x, and then you multiply by the derivative of the inside, which is 2. Now this one you're going to have to clean up a little bit, so this is negative 2 sine of x plus 2 cosine of 2x. Now you're going to have to set this equal to 0, but as it sits, that's not something that's very easy to solve. We're going to have to go back when we did the trig review and we went over all of those identities for the double angle of cosine. There's 3 of them, but only one of them has signs uniquely in it. So I'm going to go back to my identities and I'm going to plug that in. This would be negative 2 sine of x plus 2, and if you go back to your identity review, cosine of 2x has an identity that says 1 minus 2 sine squared of x is equal to the cosine of 2x. Distribute that 2 through, so negative 2 sine of x plus 2 minus 4 sine squared of x equals 0. Now, a couple things you can do here. You can rearrange your terms if you want to on the left-hand side and then figure out what to do from there. I'm actually going to do it that way. You could also move some things around to the other side, but that's kind of an overkill. So I'm actually going to write this as negative 4 sine squared minus 2 sine x plus 2 is 0. They all have a great common factor. They all have a 2 in common, but also I'm thinking ahead. I want that sine squared term to be positive, so not only am I going to factor out a 2, I'm going to also factor a negative out of everything as well to make this 2 sine squared x plus a sine x minus 1 equals 0. And while the negative 2 doesn't change, you are now able to factor the trig quadratic as we've done a few times throughout this semester. So this should factor into 2 sine x and sine x. It should be 1 and 1, and I believe to get the plus sign on the inside, you should have minus first and plus second. All right, finally, you can solve for your angles, or your x values here. So set everything equal to 0. You don't have to do the negative 2 because negative 2 can't be 0. So 2 sine x minus 1 is 0, and sine x plus 1 is 0. On the first one, if you add 1 to both sides, you get sine x equals 1, 2 sine x equals 1, and then dividing both sides by 2, you get sine x is 1/2. On the second one, only one step, if you subtract 1 from both sides, you get sine is negative 1. Now the good thing I noticed up here is that the interval that they gave us, which is 0 to pi over 2, that is talking about quadrant 1. So we only care about the angles that make this positive. Sorry, let me rephrase that. We only care about the angles that are in quadrant 1 that satisfy these. Now the good thing about quadrant 1 is that your A quadrant, everything is positive. There's no way sine can be negative 1. So I'm not even worried about that second one. On the first one, if you're looking in quadrant 1 and asking yourself, where is sine 1/2, that occurs at the angle pi over 6. So after all of that trig work, you finally get to make your t-chart. You have x and y. So in this case, the only critical number that you found that worked was pi over 6. And then you also have your endpoints, which are 0 and pi over 2. Now, if you plug these values in, so if I plug pi over 6, now this one I'm actually going to write out because it's a little bit harder to do in your head. So we're going to have 2 cosine pi over 6 plus the sine, and if you double pi over 6, that's pi over 3. So this would be 2 times the square root of 3 over 2 plus the square root of 3 over 2, which is equal to root 3 plus root 3 over 2, which is 3 root 3 over 2. If you plug 0 in, this one's a little bit easier. Cosine 0 is 1, sine of 0 is 0, so 2 plus 0 gives you 2. And then pi over 2 is also a nice one to plug in because the cosine of pi over 2 is 0. If you double pi over 2, that's going to be pi. Sine of pi is also 0, so since both of those are 0, they are 0. Now what you're probably noticing is that 0 is pretty easy to notice. That is obviously your smallest y value, so we'll call that your absolute min. And then if you're trying to figure out which one of those is bigger, like I say, you can get your calculator out if you need to. So let's see, 3 root 3 divided by 2 is about 2.59. So 2.59 is obviously bigger than 2. So that is going to be your absolute maximum value. All right, and then to wrap up this first section, just a couple little sketches here that I want to see if you can notice the difference in. So both these examples kind of say the same thing, only I add an extra word in the last one. Example 3 says, can you sketch a graph of a function that has a local maximum at 2 and is differentiable at 2? And on number 4, same thing, except I want it to be non-differentiable. So the easy thing here is that if I just kind of draw myself a little X and Y chart. So when it says 2 this time, you see the word at there is very critical. It's talking about X equals 2. So I'll just kind of draw my 1, 2 there. So I want a local maximum, so that means it has to go up and then come back down, but I want it to be differentiable. So that means if you go back to when we talked about differentiability early in chapter 2, it has to be continuous, it cannot have a sharp point, and it cannot have a vertical tangent. So something simple to be would be something like, let's go up, back down, and then something like that. Once again, my sketch is not perfect, but at 2, or what I meant to be 2, that is your local max. It goes up and back down, but it's not the highest point, but it is differential. It's a nice smooth curve. Versus if you want to draw something very similar, so go to X equals 2 again. I want it to be a local max, but I want it to also not be differentiable. So what about something like this? What if I draw kind of like a sharp point, and then something like this, something you could see from maybe a piecewise function, because if you look at your point there, that is a local max. It goes up and comes back down, but since it has a sharp point, it is not differentiable at X equals 2. So that wraps up section 3.1. Big ideas there, critical numbers. We're going to see that again in the next video. We'll see it again in this section as well, but a lot in the next video. And then knowing how to find absolute maximums and minimums. So in this section, we're now going to look at a very popular theorem called the mean value theorem. Now, the mean value theorem is a very general theorem that we're going to talk about what it means in a few minutes. But before we do that, we're actually going to look at a more specialized case of the mean value theorem, which is a lot easier to do, and it's called Rolle's theorem. So let's talk about what Rolle's theorem says. So Rolle's theorem says, let f be a function that satisfies the following 3 hypotheses. It is continuous on a closed interval a to b. We just talked about that in the last section. It's differentiable on the open interval a to b. And the big one, number 3, this is what makes Rolle's theorem special. F of a and f of b have to be the same thing. So when you plug both endpoints into the function, you should get the same y value. If this is true, then there has to be a critical number somewhere in the interval such that the derivative equals 0. No ifs, ands, or buts. If the endpoints equal each other and you can say it's continuous and differentiable, then you can find a critical number somewhere in the interval. So as you can see from these 4 graphs that I pulled out of the book down here, on all 4 of these graphs, you can see that your f of a, which means the endpoint values, f of a and f of b are the same thing. They give you the same y value. Now, a bunch of things can happen here. Most of the ones we're going to see are this one, and this one, where there's obviously a local, well, it could be an absolute max, I guess, in this case, but we'll call them locals just to make it general. There's going to be a maximum and a minimum somewhere between A and B. You could have one or the other, as you can see on the right-hand graphs. You could have both, as you see on the bottom left-hand graph. And then very, very rarely, you could actually define this as being a straight line, and that means every number in between the two endpoints is a critical number because every line has a horizontal point. So what I want to do here is, before we get to mean value theorem, let's run through a couple examples of what Rolle's theorem tells us. So example number 1, verify that the function satisfies the 3 hypotheses of Rolle's theorem on the given interval, then tell me all the critical numbers that satisfy the conclusion of Rolle's theorem. So what if we do f of x equals 3x squared plus 12x minus 2? So the 3 parts of Rolle's theorem say, is it continuous? Well, the answer is yes here because it's just a nice simple polynomial function. There's no domain restrictions. Number 2, is it differentiable? Well, the answer once again is going to be yes here. If you take the derivative of this, which we're going to see here because we need it, we'll go ahead and write it out. F prime of x is equal to 6x plus 12. Your question is, to answer part 2, is there any number x you cannot plug in? And the answer is no. Any x number you plug in, you will get a value that satisfies the derivative. So part 3, does f of a equal f of b? So right here below, f of a is going to be f of negative 4. F of b is going to be f of 0. If I plug negative 4 into the original function, let's see what happens. Give me a second to write it out. Negative 4 times negative 4 is 16, and 16 times 3 is 48. 12 times negative 4 is a negative 48, and then minus 2, so we get a y value of negative 2. And then if I go through and plug 0 into all of the same x values, the zeros all go away and you're good. You got negative 2 on both of them. So that means Rolle's theorem works. So what Rolle's theorem says is that if you take the derivative from part 2, which is 6x plus 12, if you set it equal to 0, the answer should be somewhere between the interval that from the beginning. Let's see. If I subtract the 12 over, 6x equals negative 12, and if you divide both sides by 6, you get x equals negative 2. And negative 2 is in between the two numbers that you were given. If it's not, either it doesn't satisfy Rolle's theorem or you solved the derivative incorrectly. So double check both of those before you freak out. Let's do a trig one. Like I said, I try to mix trig in when I can. Can you verify once again that Rolle's theorem is good? Does all 3 parts satisfy? And then can you find the values in the interval that satisfy the definition of Rolle's theorem? So let's do the sine of x over 2 on the interval pi over 2 to 3 pi over 2. So going through our 3-step process, example number 1, is it continuous? Well, the answer is yes, because if you were to draw a sine wave like you do in a trig class, there are no asymptotes on a sine graph, so therefore it exists everywhere. Step number 2, is it differentiable? Well, take the derivative and let's find out. The derivative of sine is cosine. You'll leave the x over 2 alone, but since it's a chain rule problem, you take the derivative of the inside, the derivative of x over 2 is 1/2. Cosine, just like sine, has no vertical asymptotes anywhere on its graph, so therefore any x value you plug in will work, so it is differentiable. Step 3, does f of a equal f of b? So let's check that. That means I'm going to do f of pi over 2, and I have to do f of 3 pi over 2. If I plug pi over 2 into this, that means you got to cut it in half because it's x over 2. Half of pi over 2 is pi over 4, and that's a very popular value. Sine of pi over 4 is root 2 over 2. If you plug 3 pi over 2 in, once again, you got to cut it in half because of the x over 2. Half of 3 pi over 2 is 3 pi over 4. And since sign is also positive in quadrant 2, which is where 3 pi over 4 is at, you will also get root 2 over 2. So great, your endpoints check out. Rolle's theorem now says is that if I take that derivative, 1/2 the cosine of x over 2, and set that equal to 0, it should happen somewhere between these endpoints. Well, to get rid of the 1/2 in the front, I can double both sides and get cosine of x over 2 equals the double of 0 is still 0. Now, normally you could say, oh, I know where cosine is 0 at, and that's good. So you can take x over 2, and cosine is normally 0 at pi over 2 and 3 pi over 2. But since I got to solve for x, I now need to double everything. So I'm going to multiply everything by 2. And that's going to give me an x equals a pi and a 3 pi. Now, just because you get a bunch of answers does not mean they're all correct. You can only use the answers that are in the interval you're given. 3 pi is too big, but 1 pi is in between 1 pi over 2 and 3 pi over 2. So x equals pi is your only value that satisfies Rolle's theorem here. But before we move on to mean value theorem, to show you an example of where Rolle's theorem does not work, let's look at this one. What if you have a function like 1 minus x raised to the 2/3? Can you show me, and here's what I'm kind of scared of, a lot of students just assume that they can jump straight to part C, and if that works, you're good. So I'm going to show you this example where part C is going to work. F of -1 and f of 1 are going to be the same thing. But why is there not a number between them that satisfies Rolle's theorem? So let's talk about that. Here's what I see a lot of students do. So they're given the interval -1 to 1, and the first thing they do is they jump straight to the last part, assuming that's enough, and they plug both endpoints into the function. That would be 1 minus -1 to the 2/3, which is 1 minus 1, which is 0, and then 1 minus +1 to the 2/3 is also 1 minus 1, which is 0. So students assume that Rolle's theorem works. Here is the problem. On part 2, so I'm going to jump to part 2, find the derivative of this function. The 1 goes away. Negative x to the 2/3 becomes -2/3 x to the -1/3. If I rewrite this, move the x to the bottom and make it positive, this is -2 over 3 x to the 1/3. Here's where the problem comes in. Part 2 says you have to be differentiable, which means that when you take the derivative, every x value has to work in the interval. But that's not true here. This x on the bottom is not good. That x cannot be 0. And since 0 is in between -1 and 1, that is a problem. That means that this does not contradict Rolle's theorem. This simply says that Rolle's theorem cannot be applied. So just be careful, don't fall into that laziness of students that I see all the time who just jump straight to part C, assume that if the endpoints are the same, they can do Rolle's theorem. Make sure you double check that you are continuous and differentiable on the interval. All right, and finally, to wrap up this video, we're going to move to the more generalized form. So let's look at mean value theorem. What mean value theorem is that it's different from Rolle's theorem because that third part is not true. You're going to see that a lot of functions, the endpoints don't give you the same y values. So we need a way to be able to find critical numbers in relationship to the endpoint values. So what the mean value theorem says is let f be a function that satisfies the following two hypotheses. F is still continuous and f is still differentiable. We're still going to check that every single time. But now the critical number is not going to equal 0. Instead, your critical number, which is f prime of c, now has to equal f of b minus f of a over b minus a. Or there is a second formula down here. I'm going to put little stars by it. I don't use that formula, but it's there if you would rather use it, but that is where it's coming from. So what does this mean graphically? So if you look at these two graphs, what mean value theorem says is that if you take the two endpoints and you find the slope between them, which is what we're going to do, that's the f of b minus f of a over b minus a, that's m. There has to be a point somewhere between a and b, we're going to call that our critical number c, where there has to be a number where the slope of the tangent line comes out to be the exact same thing, whether it be a negative slope or whether it be a positive slope. And even sometimes, as you can see on the second graph, when I found the slope between a and b, so that would be this m, there are some times that there are multiple points that create the same slope of a tangent line. I think I have one example of that we're going to see in a few minutes, but that's the difference. Versus the slope being horizontal, we now need the slope to match the slope between the endpoints. So let's do a couple examples. Number 4, verify that you can actually do the mean value theorem by checking the two hypotheses and then find the number c that satisfy the conclusion of the mean value theorem. All right, so step number 1, is it continuous? Well, your original function is just a polynomial, so I know that there's no domain restrictions there. Step number 2, is it differentiable? So I'm going to take the derivative of my function, which is 4x minus 3, and there's not a single x value that you can give me that doesn't work by plugging it in. So good, we are continuous and we are differentiable. So what does mean value theorem say again? So let me write it over here in blue. It says that f prime of c has to equal f of b minus f of a over b minus a. Well, this part we already did. We already found the derivative. I need to find the right-hand side. So in green, I'm going to find this. In this case, a is 0 and b is 2 because that's the two endpoints of your interval. So we're going to do f of 2 minus f of 0 all over 2 minus 0. So get your calculator out or do it by hand. If you plug 2 into the original function, let's see, that's 4, 8, 6, that's 3, minus, if you plug 0 into the original function, you should get 1, and then 2 minus 0 is 2. This gives us 2 over 2, which is 1. This 1 gets plugged into the right-hand side of the mean value theorem. So back over here in red, you can now take the derivative of your function, which we found to be 4x minus 3, and I'm going to set it equal to the number we found for the right-hand side. Add the 3 to both sides, so 4x equals 4. Divide both sides by 4, you get x equals 1. This 1 should be inside of the interval 0 to 2 from the beginning, and it is. Check mark. X equals 1 is the only critical number that creates the slope of a tangent line equal to the slope between the endpoints. That is what the mean value theorem tells us. I couldn't find a good trig problem, so you're off the hook for right now, but I did find a second example that illustrates this. I believe this is the one that has multiple answers, so let's see this. What if you're given f of x equals x cubed minus 3x plus 2 on the interval negative 2 to 2? Verify that you can do mean value theorem and then find the values that satisfy mean value theorem. Step number 1, is it continuous? Well, once again, yes, because it's just a polynomial function. And step number 2, is it differentiable? So f prime of x is going to equal 3x squared minus 3, which once again is also a polynomial, so we are differentiable everywhere. Need to do the right-hand side of mean value theorem. So the right-hand side says you have to find f of b minus f of a over b minus a, which a is negative 2, b is positive 2. So this is f of 2 minus f of negative 2 over 2 minus negative 2. All right, so that's going to end up being, let's see, if you use your calculator, do some mental math. If you plug 2 in, that's 8 minus 6. 2 plus 2 is 4. Minus, if you plug negative 2 in, that's negative 8 plus 6 is negative 2. Negative 2 plus 2 should give you 0. Over 2 minus a negative 2 is 4. And just by coincidence here, we get the same number as the last problem. That's going to be 1. Take the 1, take the derivative, and set them equal to each other. So 3x squared minus 3 needs to equal 1. If I add 3 to both sides, 3x squared is going to equal 4. Divide both sides by 3, you get x squared is 4/3. And if you take the square root of both sides, remember plus and minus, the square root of 4 is 2. We don't know root 3. And you can verify with your calculator if you need to, but both of these numbers are good. Both of these numbers are in the interval that you were given. So this is an example where there are 2 different numbers that give you the slope of a tangent line that's equal to the slope between the endpoints. And last but not least in this video, I wanted to give you kind of a thinking question to show you how you can not have a function but still kind of play with some of the parts of mean value theorem. So example number 6 says, if f of 1 is 10, and f prime of x is always bigger than or equal to 2 for every x on the interval 1 to 4, how small can f of 4 possibly be? So you're trying to figure out what f of 4 is. Now, since they did give us an interval and they did not give us enough information to verify Rolle's theorem, I'm going to start off with the idea of mean value theorem that says f prime of c has to equal f of b minus f of a over b minus a. Now, what do we know here? I know a is 1, b is 4, and I know f of 1 is 10. So f of a is 10. Your f prime of c, that's the number that you do not know technically. But what you do know is what is the smallest that f prime of c can be. Since you're trying to make f of 4 as small as possible, you need to make your derivative as small as possible as well. Well, from the interval they gave us, the smallest that your derivative can be is 2. So for my derivative, I'm going to plug 2 in. F of b is going to be f of 4 minus f of 1 all over 4 minus 1. Well, plugging in the other number that I know, since I know what f of 1 is, I can now turn that into a 10, and 4 minus 1 is 3. If you multiply both sides by 3, you should get 6 equals f of 4 minus 10. And then if you add 10 to both sides, 16 is f of 4. So if I force the derivative of c to be as small as possible, that means that I can let f of 4 be equal to 16, and that's the smallest value, because any value of f of 4 that you make bigger than 16 is going to end up making the f prime of c larger, and that means bigger than 2, and that's not what you want. So that is the end of this video. So that ends sections 3.1 and 3.2. So a quick little recap. We learned how to find critical numbers. We learned how to find absolute max and mins. We talked about local maxes and mins, and then we also did Rolle's theorem and mean value theorem in 3.2. In the next video, we're going to go back to the idea of local maxes and mins, and we're going to do some more problems of showing you how to find those. That's a little bit more difficult. So in the next video, which is sections 3.3 and 3.4, we will look at local maxes and mins.